Hello friends, welcome to the video lecture of engineering physics. Friends, this is my second lecture on unit number 4, that is semiconductor physics. In this video lecture, we are going to discuss the conductivity of semiconductors. Now, what is meant by semiconductor? The material whose electrical conductivity lies between the conductor and insulator. That material is considered as semiconductor. So, in this video lecture, we will discuss about the conductivity of semiconductor and we derive an equation for the conductivity of semiconductor. For the derivation of equation for conductivity of semiconductor, we consider a semiconductor of length L with cross section area A. Let a voltage V be applied across the semiconductor. When the current flowing through the semiconductor is due to the charge carriers such as electrons and holes as shown in figure. So here friends, this is total semiconductor whose length is considered as L. A voltage is applied across the semiconductor so that electrons are attracted towards the positive terminal, whereas the holes are attracted towards the negative terminal. Electrons are negatively charged particles, whereas holes are considered as the positively charged. So electrons are moving towards the positive terminal and holes are moving towards the negative terminal. So in this semiconductor, the current flowing through it is due to the electrons as well as hole. Let we consider some parameter like n is equal to n for be the density of electron in conduction band, that is number of electrons present in the conduction band we consider as n. Then p is density of the holes in valence band, that is number of holes present in the valence band. Then mu suffix e, which is considered as the mobility of electrons. Similarly, mu h is for mobility of the holes. Then VE, that is drift velocity of the electron. Drift velocity means the velocity with which electrons are moving towards a single or towards a particular direction. That velocity is known as the drift velocity of that electron. So we consider VE as the drift velocity of electrons. Similarly, VH as the drift velocity of the holes. Now, as we know that the total current flowing through the semiconductor is the total charge crossing the volume per unit time. So the total charges which are crossing the given volume of the semiconductor per unit time is nothing but the total current flowing through the semiconductor. So as we know that in semiconductor, the current flowing through it is due to the electrons and holes. So that total current we consider as a capital I, which is equal to the current flowing due to the electron as well as current flowing due to the holes. So I is equal to IE plus IH. E for electron, H for holes. Then as we know that current flowing through any given volume is nothing but number of electrons into charge on that electron into velocity of that electron and area of the given material or area of the given semiconductor. So we put the values of we put the equation for the current flowing due to the electrons as well as due to the holes. So we write this equation as I is equal to N E into VE into A plus in second bracket P, that is number of holes, into E, charge on the holes, into VH, that is drift velocity, into area A. So from this we take E and A common, so we can write this as I is equal to E into A into bracket N into VE plus P into VH. We call this as equation number 1. But as we know that the drift velocity of the electron depends on the applied electric field. So V is directly proportional to E, or we can write this as V is equal to mu E into E, where this mu E is constant and this constant is known as the mobility of the electron. So for electron it is taken as a mu E. Then again we know that electric field is defined as E is equal to V divided by L. Then we put the value of this electric field. So we can write VE is equal to mu E into V divided by L. Similarly for holes, VH is drift velocity of the holes is equal to mu H into E, which is equal to mu H into V divided by L. Putting the values of VH and VE in equation 1, we get I is equal to EA into bracket N mu E into V divided by L plus P into mu H into V divided by L. Again here V by L is common, so we take outside the bracket. So I is equal to EA into EA V divided by L into bracket N into mu E plus P into mu H. We call this equation as equation number 2. Then rearranging the terms, V divided by L is equal to L divided by A into 1 upon E into bracket N into mu E plus P into mu H. But according to the Ohm's law, the ratio of voltage and current is nothing but the resistance of the semiconductor. So V upon I, we take it as R, resistance of the semiconductor. So R is equal to L upon A into 1 upon E into bracket N mu E plus P into mu H. Or we can write this equation as R is equal to rho into L upon A. We call this as equation number 3. Now in this equation we introduce a new parameter, that is rho, which is equal to 1 upon E into bracket N into mu E plus P into mu H, which is nothing but the resistivity of the semiconductor. Now in this article we have to derive an equation for the conductivity of semiconductor. Then conductivity of semiconductor is nothing but reciprocal of the resistivity of that semiconductor. Therefore the conductivity of the semiconductor is sigma, which is equal to 1 upon rho, is equal to E into bracket N into mu E plus P into mu H, bracket complete. So this equation we call it as equation number 4. So this equation 4 gives the conductivity of the semiconductor. So this equation is general equation for conductivity of the semiconductor. But we know that semiconductors are divided into two different types. First is intrinsic semiconductor and second is the extrinsic semiconductor. We derive an equation for the intrinsic conductivity of intrinsic semiconductor as well as conductivity of extrinsic semiconductor. So first we consider conductivity of intrinsic semiconductor. So again, what is meant by intrinsic semiconductor? The semiconductor which is in pure form, that semiconductor is known as the intrinsic semiconductor. For example, germanium, silicon, these are the pure form of semiconductor. So these semiconductors are called as intrinsic semiconductor. Friends, as we know, in intrinsic semiconductor, number of free electrons are same as that of the number of holes. That means free electrons and number of holes are equal in the intrinsic semiconductor. So we can write this as N. N means the number of free electrons. P, number of holes. So N and P both are equal, and for this we call the another symbol as Ni, I for intrinsic semiconductor. Therefore conductivity of an intrinsic semiconductor is sigma is equal to E into bracket Ni into mu E plus Ni into mu H. Then Ni taken common, so sigma is equal to E Ni into bracket mu E plus mu H. We call this as equation number 5. This equation 5 gives the electrical conductivity for the intrinsic semiconductor. Then we go further for second type of semiconductor, that is extrinsic semiconductor. So conductivity of extrinsic semiconductor. Now what is meant by extrinsic semiconductor? So we discussed the intrinsic semiconductor, the semiconductor which is in the pure form. Then to increase the electrical conductivity of the intrinsic semiconductor, some impurity is added in the pure form of semiconductor. then this new semiconductor is formed. That semiconductors are known as the extrinsic semiconductors. So in this extrinsic semiconductor, pentavalent or trivalent impurity is added to increase the electrical conductivity of the semiconductor. So depending on the impurity added in the pure form of semiconductor, extrinsic semiconductor is again divided into two types of semiconductor. One is N-type semiconductor and second is P-type semiconductor. When the pentavalent impurity is added in the pure form of semiconductor, then that semiconductor is considered as N-type semiconductor. When the pentavalent impurity is added, then pentavalent impurity contains 5 valence electrons. Among these 5 valence electrons, 4 electrons are make covalent bond with the neighboring atom and 1 electron is remain which is free to move in the semiconductor. So there are large number of atoms, so large number of free electrons are present in the N-type semiconductor. Again, as we know that for N-type semiconductor, number of free electrons are more than number of holes, that is hole concentration is negligibly small. So we can neglect this hole concentration. Let we consider Nd as the concentration of donor atom. So sigma is a general equation of conductivity of the semiconductor is sigma is equal to E into bracket N into mu E plus P into mu H bracket complete. But in this N-type semiconductor, number of free electrons are very large as compared to the holes. Therefore, the product of N, that is number of electrons and mobility of the electron, this product is very large as compared to the product of number of holes and mobility of that holes. So we can neglect this second term P into mu H. So we get the equation sigma is equal to E into Nd. Nd is the concentration of donor atoms into mu E, mobility of the electron. So this equation called as equation number 6. This equation 6 gives the conductivity of N-type semiconductor. Then second type of semiconductor, that is P-type semiconductor. When trivalent impurity is added in the pure form of semiconductor, then the semiconductor is known as P-type semiconductor. In trivalent impurity, there are three valence electrons. These 3 valence electrons make covalent bond with the neighboring atom, but there is one deficiency remain, that is considered as a hole. So in P-type semiconductor, number of holes are large than the free electrons, that is free electron concentration is negligibly small in P-type semiconductor. Here these additional electrons is accepted, so it is considered as the acceptor impurity. So we consider let Na is equal to concentration of the acceptor atom. Therefore the conductivity of P-type semiconductor is sigma is equal to E into bracket N into mu E plus P into mu H. But here P is very large than N, that is number of holes are very larger than the number of free electrons, and P into mu H is also very larger than the N into mu E. So we can neglect the first term, that is N into mu E of this bracket. So we get finally sigma is equal to E into Na into mu H, where E is the charge on holes, Na is the concentration of acceptor atoms, and mu H is the mobility of the holes. This equation we call it as equation number 7. So equation 7 gives the electrical conductivity of P-type semiconductor. So in this way we find the general equation of electrical conductivity for the semiconductor, and from this equation we derive the equation for intrinsic semiconductor, N-type semiconductor and P-type semiconductor conductivity. Okay, thank you.